Hi, and welcome to the video on chemistry and proportions. Before we begin, I just want to briefly talk about proportions or ratios. They are super easy, and that's because we use them all of the time. A lot of times we do this without even thinking about it. So whether you're baking and you want to scale up or scale down a recipe, or you're in a grocery store, or you're building something and you need to change the amount of materials that you have, we oftentimes use proportions or ratios. So that makes them a useful tool. Now it's important to know that there are different ways to set them up. In this video, we're going to look at three methods. The first is scalar. The scalar method is super conceptual, and it's something that we oftentimes use when we're doing mental math. And then the last two, proportion methods 1 and 2. Both of these methods involve setting up fractions, setting two fractions equal to one another and solving using cross multiplication. In the end, though, we are going to focus on proportion method 2. This setup is important because oftentimes in the field of stoichiometry, which is what we're studying at this point, we utilize the molar ratios as seen in proportion method 2 when we're solving things using dimensional analysis, which is the method that is often used. Often proportion is not used to solve stoichiometry problems, but proportion method is important because it's super conceptual. So let's take a look at the scalar method. If you have a problem like this, how many eggs are there in 1.25 dozen, you can probably solve that mentally and do a little mental math, and you would say, oh, there are 15 eggs in 1.25 dozen. So what is your brain doing exactly? The number of eggs is your unknown, and the dozen that you have there is 1.25 dozen, so the amount you have is 1.25 dozen. What you know is that 1 dozen is equal to 12 eggs, and what you're trying to find is how many eggs are in 1.25 dozen. So what you do when you're doing mental math is you figure out, well, what do I need to multiply 1 by to get to 1.25? And that number is clearly 1.25. So if you multiply the 1 by 1.25, that will give you 1.25 dozen. So you do the same thing on the other side. You multiply the 12 by the 1.25. And that will tell you the number of eggs. And so when you do the math, 12 times 1.25 will give you 15. And so that's your final answer. Let's look at how we can do the same problem with proportion method 1, which is very conceptual. So we already have our problem annotated, which is a super important step in solving these problems. In proportion method 1, we take the information that we know again, 1 dozen is equal to 12 eggs. And we take the information that we find, 1.25 dozen is equal to X number of eggs. And what we do is we set this into two fractions by drawing fraction lines between our values. Notice in this case we have dozen on top of dozen and eggs on top of eggs. Okay, once we have that information, then we can cross multiply, because whenever you have two fractions set equal to each other, you can cross multiply to solve for X. So the next line down I have X times 1, or 1 times X, and that's over here, and 1.25 times 12, and that's over here. To solve for X, I need to isolate it, so I would divide both sides by 1, and that will give me X is equal to 15. So this is the math that we would do for proportion method 1. This method is pretty conceptual. Again, you're taking the two equations and then turning them into fractions and then solving using cross multiplication. All right, the last method, proportion method 2, it's again more useful for dimensional analysis. So again, we already have our question annotated, and how do we use this method to solve? We know that we have that 1 dozen is equal to 12 eggs. That's what we know. And we're trying to find how many eggs are in 1.25 dozen. Great. We are also going to turn these into fractions, but we're going to do it in a different way. We're going to take this first equation of the things that we know and turn that into a fraction. So I'll show you what that looks like. We take 1 dozen and we're going to put it over 12 eggs, and that's where we get our first fraction. Then we're going to do the same thing with the second equation that we have over here, our find equation, and we're going to take 1.25 dozen and put it over X numbers of eggs. Okay? Once we have that, we set an equal sign in between the two fractions because because we know that if one doesn't have 12 eggs, then 1.25 dozen will have a certain number of eggs that match that ratio. Now it's time to solve. Once you have your setup, your two fractions set up, you can go ahead and solve. So again, we're going to use cross multiplication. We multiply across here, so x times 1 or 1 times x, and 12 times 1.25. And then of course the math looks the same. Okay, and so we get the same answer. All right, so you just saw three methods. The scalar method, proportion method 1 and 2. We are now, for the rest of this video, going to focus on using this method, proportion method 2, for solving problems from our Unit 5 Day 4 packet. So you might want to get that up. This is CFU 2A from the Unit 5 Day 4 packet, and it reads, a glass of water contains 20 moles of water molecules. How many water molecules does it contain? So as with anything, I want you to begin by annotating the information. This value here, 20 moles, that tells us the moles is equal to 20. And notice that for the unit for moles is MOL. We basically just drop off the E for the unit of moles. And how many water molecules does it contain? So we're looking for the number of molecules. Okay, so let's take a look at the information that we know and are trying to find. Since we're relating moles to the number of molecules, our know is the equation that 1 mole is equal to 6.02 times 10 to the 23 things. In this case, a thing will be molecules. And what we're trying to find is how many molecules are in 20 moles. So those are the two equations. Now the first step is to, or the next step is to take the know equation and the find equation and turn them into fractions. So let's do that with the know first. I take this information, 1 mole, and I put it over 6.02 times 10 to 23 molecules. I do the same thing with the find. I take the find information and put it, which is 20 moles, and put it over x molecules. And then set them equal to each other. Now before we proceed on, it's really important to note that notice how we have the unit of mole in the top here, in the numerator of the first fraction. We also have it in the numerator of the second fraction. It honestly doesn't matter if you put molecules on top or moles on top in the first fraction, as long as you do the same thing in the second fraction. So your units have to match. Moles on top, moles on top. Okay, once we have our two fractions set up, we can go ahead and solve using cross multiplication. So here are our fractions again. They're set equal to each other. I'm going to cross multiply, and I have 1 times x, so that gives me this information here. 20 times 6.02 times 10 to 23, which gives me that information there. I want to isolate my x, so I'm going to divide both sides by 1. And when I do that, I get this number here. X is equal 120.4 times 10 to the 23. Or if you want to write it in scientific notation, 1.204 times 10 to the 25. If you're confused on that, you want to go back to the homework assignment on scientific notation and see how I got these answers. If you need help on how to put this information into your calculator, please see me. Okay, so that's our answer there. And so we would say, in addressing this answer, there are 1.204 times 10 to the 25 water molecules in 20 moles. Let's look at one more example with the number of molecules in moles equation. Take a moment to read this information out. Okay, so this is from CFU 2B. It says a diamond contains 1.38 times 10 to the 24 carbon atoms. How many moles of carbon does it contain? Okay, so let's go ahead and annotate this information, and just we know that this is the number of atoms, and that we have that value, 1.38 times 10 to the 24, and we're asked how many moles, so moles is our unknown. Okay, since we are comparing moles to the number of things, in this case is atom, the equation that we're going to use is that 1 mole is equal to 6.02 times 10 to the 23. This says molecules, it should say atoms. Okay, so now that I've corrected that, we can resume. All right, so Since we're relating the number of atoms to moles, we're going to use 1 mole is equal to 6.02 times 10 to the 23 atoms, and we know that. And we're trying to find the number of moles in this number of atoms, 1.38 times 10 to the 24. So again, I'm going to take the know equation and turn it into a fraction and the find equation. Let's see what that looks like. Great. So now that we have our two fractions set up, we are ready to solve using cross multiplication. If you feel confident in doing that, you can pause the video now, and when you press play again, you'll see my work. Okay, great. So we have our 1 mole over 6.02 times 10 to the 23 atoms and x moles over 1.38 times 10 to the 24 atoms. We cross multiply x times 6.02 times 10 to the 23, that gives me this value over here, and 1 times 1.38 times 10 to the 24, that gives me that value over here. To isolate my x, I'm going to divide both sides by 6.02 times 10 to the 23. That will cancel this out on that side, and then that will give me x is equal to 0.229 times 10 to the 1 power, or if you're writing this in appropriate notation, in standard notation, it'll be 2.29 times 10, 2.29, which will be the final answer there. So in answering this question, we'll say that there are 2.29 moles in 1.38 times 10 to the 24 carbon atoms. All right, I would recommend before you proceed on to redo CFU 2C and 2D from that same packet. And when you can pause the video now, and when you press play again, there'll be the answers shown on the screen. Okay. All right. We are now going to look at cases where we're using molar mass, and we're going to begin with CFU 7A from that day 4 packet. So you need to take a moment to turn there. Go do so now. In that CFU, it asks a piece of copper wire weighs 11 grams. How many moles of copper does it contain? So in this case, we are comparing mass to moles. And for that, we're going to have to use the relationship or the equation that 1 mole is equal to the atomic weight of the atom, in this case, that we're looking at. And we get the atomic weights from the periodic table. If you need help with that, you can watch the video on atomic weight and molar mass. What we're trying to find is the number of moles in 11 grams. So again, we have our two equations, our known and our find. We take our known, we convert it into a fraction. Why don't you try it? Press pause, and when you press play again, you'll see what my work looks like. Great. Let's do the same thing with the find. We're going to convert that into a fraction. So press pause and we press play again. You'll see what my work looks like. Cool. Okay, so we have our two fractions. We can set them equal to each other, and now it's just time to solve using dimensional analysis. All right, here are the two fractions again. Notice once again that if you have moles in the numerator, you have in one fraction, you should have in the numerator of the other. Your units have to match up. Grams in the denominator, grams in the denominator. Go ahead and solve using cross multiplication, and then when you press play again, you'll see my work. Cool. So after cross multiplying, we have x times 63.55 and 1 times 11. To isolate our x, we divide both sides by 63.55, and then we get x is equal to 0.173 moles. And so the answer here is that there are 0.173 moles in 11 grams of copper atoms. And this says carbon, but that should say copper. That's what the problem asked. All right, the last one, I'm just going to show you a setup for it. In this case, it's a container of table salt, NaCl, which weighs 737 grams. How many moles of NaCl are in the container? Again, we know our mass. We're looking for our moles in this example. But it's important to know that NaCl is a molecule. I know that because there's more than one atom. So in this case, I'm going to have to calculate the molar mass.